Hello, class. Welcome to the lecture on mobile app security. Uh, in this course, we will only be focusing on Android app security. We will not be looking at the topic of iOS app security, which is a completely different set of concepts. Okay, so we are only going to be looking at Android app security. Um, this also reflects the amount of activity that goes on in the community. Primarily because Android is an open platform, there has been a lot more scientific work on the Android app ecosystem rather than the iOS app ecosystem, where you'll find a relatively small number of papers talking about iOS security, probably just a handful. Whereas the number of Android app papers uh, spans almost in the hundreds. Okay, so okay. So the problem here is that mobile devices, as we saw in the last class, they're in some sense mini computers. So we are talking mainly about things like smartphones and tablets and so on. And as we studied in the last class, these apps, these devices are outfitted with various kinds of sensors like GPS, camera, accelerometer, and so on. And they have extremely powerful CPUs, almost as powerful as the uh, desktops of nearly a decade ago. They're also equipped with all sorts of communication channels, be it 3G or 4G, Wi-Fi, near field communication, and so on. Okay, so the number of devices has grown exponentially, and in some sense, uh, this is the computer that you always have with you, and it's extremely powerful. So when we talk about mobile app security, right? I mean, the question is, how is it different from standard desktop security? Well, so there are a number of differences, right? So first of all, unlike traditional desktop computers, the model over here is that you have limited computing resources, like limited amount of battery, CPU, limited amount of memory, storage, and so on. So you cannot use heavyweight uh, solutions that are applicable for the desktop environment for your mobile device. So, for example, one solution that is used in the case of desktop based machines for detecting malware is to use hypervisors and virtual machines. Okay, the virtual machine is scanned by the hypervisor. You can detect rootkits, and we studied this in class. So this solution is not readily applicable for things like mobile devices, primarily because there's a lack of mobile virtualized environments that are widely deployed, and also it is a pain to uh, have such a virtualized environment on your phone, even if it does exist, right? Because it's going to consume battery and CPU um, resources on the resource limited uh, mobile devices. Okay, so that's one really big reason why you cannot just use mobile device, desktop security solutions on your mobile device. The second really big factor is that of the variety of users, right? As compared to the desktop environment, where you know typically it is people who are working on computers or are somewhat computer literate that end up using the desktop machine. In contrast, the smartphone and the mobile phone is much more ubiquitous. Almost everybody has it, and so there's a wider variety of uh, of experiences in the user base, and so this also may include classes of people that are more prone to social engineering attacks. Okay, they might not be as tech savvy. They might not be as familiar um, with uh, uh, the attacks in cyberspace. Okay, So they are also ubiquitous, okay, in the sense that they are less expensive and they outnumber PCs. There are more interfaces for connectivity as well. Okay, so there are a couple of anecdotes here, and a few other points. There is another reason why it's different from PC security. In fact, two reasons that are not listed in the slide, which I would like to describe. So the first, of course, is that of the form factor, right? So unlike your desktop machine or your laptop, your mobile devices have a much smaller form factor, a smaller screen, uh, and it's a touch screen. Generally speaking, your interaction with these devices is through touch, right? And you might be reading, in fact, about various social engineering attacks that are actually enabled because of these of this different form factor. So just recently, I was reading this story, for example, about somebody who ordered, let's say, a meal on Zomato, and they got a phone call saying, "I'll send you a link. You click on it, and your food will arrive." So this person goes and clicks on it, and without her knowledge, in fact, what she has done is authorized the person who just sent the link to take some money from her bank account, right? The reason that this was enabled was because the phone's form factor is rather awkward, and you're not really checking as carefully when you click on things as you would do on a desktop environment. Okay, so the form factor is a very important contributor to security in the mobile setting. So the other factor is that in both Android as well as in the case of iOS, the major distinguishing factor is that of an app market, right? Both the iOS as well as the Android ecosystems have authorized app markets, either supported by Apple, which is the uh, Apple's App Store, and the Google Play Store, both of which have a family of apps that they support. In fact, millions of apps are supported on these app stores. And the way that apps make their way into the app store is that the application developer has got to be able to build an app, and not just build it, but also get it passed through the vetting mechanisms in both Google as well as Apple, right? Apple has its own vetting mechanism, um, and Google has its own vetting mechanism. Uh, the exact details of the vetting mechanism are not, in fact, made public. They are proprietary to both Apple as well as Google, and the vetting mechanism is the way by which apps make their way into the App Store. Therefore, if you go and download an app from the App Store, there is some semblance of security, even though there is not, as we will see. But you're at least you've got an assurance that it is not a piece of random malware that you downloaded from the internet. So there are malware for Android and iOS as well, but generally speaking, the application stores are very good at preventing traditional kinds of malware from making their way into these app marketplaces, unlike the desktop environment. Okay, so you might ask me, what is malware? Malware is things like viruses and worms, but obviously those don't exist in the Play Store or the Apple Store. So then you might ask me, what are malicious applications? And we will see that the notion of malice that we have to think about for mobile applications is different. It is not so much applications that try to do mischievous things, but rather applications that try to, let's say, steal out your data. And as we speak, of course, there is a major, uh, um, in some sense, movement going on in the internet community, and I'm sure you're also all part of it. Um, at this moment, there is a big backlash against WhatsApp, for example, for trying to collect information or supposedly collect information. And a lot of people are trying to move to other messaging applications. The reason is because, of course, related to this, right? I mean, the mobile application will share its information with some backend servers. So it's a timely topic that I thought I will mention, and we are going to be talking about how other applications will collect this data. Here, of course, the application is trying to collect data, and the big problem is in the permissions that they were asking you, right? They were asking you to agree to some conditions, and most other applications also implicitly ask you for these permissions when they present you uh, with the screen to accept the permissions. So we will see how that can lead to problems as well. Okay. So okay. So um, okay. So of course, the mobile devices. Another big difference from traditional desktop security is that mobile devices are portable because of their small form factor. Um, they are subject to loss and stealing. In fact, this is a big threat vector that exists in the mobile device space that does not exist typically in the desktop or the laptop space, where just loss of devices is a big uh, security concern. We also find that these devices have things like near field communication and magnetic stripe technology, which, when you couple with things like payment applications on these devices, uh, are becoming a major source of security concerns. Okay, so there is another aspect to mobile device security, which is that it carries some sensitive content. Obviously, your location is something that is extremely sensitive. The privacy of this you really care about. And also, there are things like payment applications, financial applications, credit cards. In fact, these days you cannot do anything in banking, at least in India, without your mobile phone. The reason is because your mobile phone is typically used as a second factor of authentication. You get an OTP, right? So, the OTP is not just sensitive, but it is also subject to loss, especially if you lose your phone. It becomes a major problem. So, the security considerations are rather different. There is also a wider range of software applications for mobile devices, primarily because the applications are small, serve a very specific purpose like a game or things like that. And there is almost a phrase these days that there's an app for it, right? Whatever you think about, there's an app for it. Okay, and these apps are all written by untrusted third-party vendors whose intentions you don't really know. They might be trying to monetize the app. They might be trying to have an advertisement based upon your activity and interaction with the app and the phone. So uh, that is a big concern. Okay, and as you can see, right, the smartphone OS market, uh, Android is a major share, right? It's around 90 percent or so. This is again, these are slightly old slides, but the trend is still the same. Windows Phone no longer exists. BlackBerry, I don't know whether it still exists, and iOS is also a major chunk, around 10 to 20%. But Android is like the really big player in this space. Okay, so this kind of motivates why we want to study Android and why there is a lot of work in the Android space. So we will look at Android um, for this lecture. Okay. It is also the case that Android gets 97% of all mobile malware, right? So if you were to go and study what fraction of mobile malware exists out there, more than 97% of malware in the uh, uh, space of mobile applications exists for Android. Okay, and what are these mobile malware? Right, so there are all kinds, right? There are Trojan horses, um, there is spyware, there is there are monitoring tools that monitor your activity, things that insert backdoors, and there are things that display ads to you, Trojan downloaders which end up downloading other bad software and so on. So that's the threat that we are looking at in the mobile space. And so when you look at mobile device security in general, there is a lot of work on things like user authentication, things like better ways to provide authentication, biometrics, and so on. There's also work on operating system and software attestation and access control permissions, an example of which, of course, we saw in the last class when we looked at restricted spaces. There's work on location privacy. Now, the problem here is rather interesting. Very often with mobile devices, you actually want to share your location so you get location relevant information. If you're using a maps application, you do really need to share your location. Um, and you might want to get location sensitive content, right? There are a lot of services available on the internet today called location based services. Unless you share your location, you cannot really avail of them. And so you have to make a trade off here in terms of either sharing your location or obtaining access to these services. There is also a lot of work on social engineering attacks and how to prevent them, and also things like covert channel attacks. And gave you many examples in the last lecture where we spoke about, the various kinds of sensors being used to leak information out of the phone. So the paper that we will cover today is going to be called TaintDroid, uh, and this is, as the name suggests, it's a taint tracking infrastructure for Android. And it says, okay, it's an information flow tracking system for real time privacy monitoring on smartphones. So this is a paper from around 10 to 11 years ago, but it's an extremely influential paper. Interestingly, just 2 months ago, OSDI 2020 was held, at which point in time this paper got the 10-year Test of Time Award. Okay, so it shows that this paper is an extremely influential paper. It has over 10,000 citations according to Google Scholar, and for very good reason. It's a very nice paper. It talks about a method to detect violations, privacy violating Android applications. Now, this paper also carries a very important lesson, right? So if you look at the date of the paper, it's 2010, and this was around the time that Android was just beginning to become popular. So 2008 was the time around which various mobile phones were released, and Android was still in its infancy, iOS was still in its infancy, and this paper was written at a time when these application markets were nowhere close to being as popular as they are today. So one big thing for this paper is that the authors had the vision to foresee that mobile devices would become extremely popular, that Android would really catch on, uh, and they investigated the privacy and the security threats in this ecosystem long, long before the ecosystem actually became popular, and the kinds of threats that were discussed in this paper became a much bigger concern, right? So oftentimes you must also work on the right kind of problem in order to have the right kind of impact. So that's a very important lesson to take away from this paper. As you will see, the methods in this paper are very similar to the methods that we have already studied in this class. So in terms of the core principles involved, there is nothing radically new. Of course, there's a lot of engineering that goes into the building of a taint-based a defense mechanism on top of a framework such as Android. Okay, so the problem that this paper solves is that applications can be installed um, on your smartphone from various kinds of application stores. Google Play, of course, is the official channel, but there are also a lot of other application markets on which you can get your uh, uh, your mobile applications. So if you go through the Google App Store, of course, your app gets installed on your Android phone. If you don't go through the Google App Store, it will ask you for permission to install the application from a third-party marketplace. Okay. So, for example, the Go Corona Go application from IISc is not something that is on the Play Store. So, if you were to try to install it, as many of you would have, you will find that you have to actually authorize the underlying operating system to install the application on the phone. Okay, so all the applications that don't actually come with the phone when you get it and that you download later on are called third-party applications. Now, third-party applications are applications that are not really installed by the phone vendor, right? The vendor is installing Android and probably pre-configuring it with some applications, but any other applications that you then subsequently download are essentially coming from third-party applications. That's what contributes to the rich application uh, ecosystem here. But because you're installing them from other sources, they are called third-party applications and they may contribute towards information leakage from your phone. So this paper tries to develop a technique that monitors when this sensitive data is being leaked, uh, and it does so in real time, right? It does not tell you after the fact. It actually prevents the data leak from happening, and it basically tracks these data flows from these third-party applications. Okay, so what can leak from your mobile device? Uh, so there are various types of mobile device information sources, right? Your you have GPS location that is tracked by your phone all the time. Every phone has something called an IMEI number that uniquely identifies the phone, and there are also, external information sources, right? I mean, for example, what apps you install and so on. So third-party mobile apps can in fact leak this information by just taking your GPS location or your IMEI number or your contacts or your location and then just send it out over the network. Now, in order to prevent this, applications have a defense mechanism, right? I mean, the Android framework has a defense mechanism. It says, look, whenever a user downloads an application, permission screen is going to be displayed to them. It's called the Android permission screen. It's called the Android manifest. The point is that the manifest file describes the set of permissions that an application is going to use. Now, you can either click yes and install the application, or you can click no if you're not okay with the permissions. But the point is that whatever permissions you authorize, only those permissions the application is going to get. So in some sense, Android is setting up a sandbox for the application and giving that application only those permissions. Okay. But what happens is that most of us are just anxious or eager to use the application as soon as possible. So we just click through, proceed, and then download the application. And the minute you set up that sandbox, the application has the permission to access all of those things. So the application can essentially intercept information sent to a source and then send it to a different destination. So it can be for all sorts of motives. You want to monitor the activity of an individual. You want to display advertisements to the individual, or you want to conduct market research in terms of, you know, what is the user purchasing, where are they purchasing it, and so on. Uh, and it can be used for identity theft and so on, right? So these are various motives for the bad guys who might want to design such kinds of applications. The question is, how do you protect against such information leakage from these applications? And this is ubiquitous, right? When you go and download an application, if you go and look at the set of permissions that the application is asking, you might also, you might very often question yourself why this application is actually asking for these permissions. Okay, so there are many challenges here. It's not that easy. The first, of course, is resource constraints, right? Uh, right, you cannot really track, as I said, whole system images of, let's say, the memory and the execution and so on, like in a virtual machine, that will be extremely expensive towards performance, and it'll consume a lot of battery. Uh, and so there are also third-party applications that are actually interested with different types of private information. And the sensitive information can be difficult to identify even when it's sent in clear format. Right? If you're looking at some 16-digit number, how do you know that it's a credit card number or not? Likewise, most location data is just a pair of floating point numbers. So even if you see that information in the clear, how do you know that it's actually sensitive data? And many applications, in fact, do share information for all sorts of useful reasons. So how do you detect which app is doing it for violating your privacy and which is not? So let's get a little bit of background on Android itself. So Android is an operating system. It's a piece of middleware that is based on Linux, um, and all of the core functionality has been written in Java and C++. So the next statement used to be true as of a few years ago, but even as recently as 2 to 3 years ago, but it's changed. So applications previously used to be written in Java and converted into something called the Dalvik executable bytecode, right? So there was a Dalvik virtual machine on which you could just execute the applications. But now there is something called the Android runtime monitor that actually runs applications, and you have to compile it down slightly differently. So things have changed. But we will be focusing on the slightly older one because that's the context in which this system was built. Right? So the Dalvik executable or the DEX bytecode executes in a Dalvik virtual machine or DVM, and applications communicate with each other via binder IPC interface. And applications communicate with each other all the time. That's one of the big hallmarks of the Android ecosystem. So, for example, you might have an application on which, maybe you want to locate a restaurant, and the restaurant locator application, you type in the kind of food that you like, and then it finds the restaurants close to you. Maybe it also wants to show you directions. So instead of building in a direction locator itself, it might just integrate with Google Maps. And so that integration essentially is a way by which the restaurant locator application integrates with a map based application to enable this kind of communication. Okay, so this happens all the time in Android. Uh, Okay, so then let's look at Binder in slightly more detail. So Binder is Android's mechanism for inter-process communication. And so all Android applications communicate with each other using this IPC binder. Okay. So in Binder, there is the concept of parcels. So parcels are the main component of the IPC framework, and they serialize the data objects before sending it out of a virtual machine. So remember, each Android application runs as its own virtual machine. This is not virtualization in the sense of entire machine virtualization, but rather virtualization in the sense of JVMs and language virtualization. Okay, so the binder kernel module, there's a kernel module, part of the OS kernel, that receives these parcels. These parcels are nothing but pieces of data where the data has been uh, complex data structures have been flattened out in some specific format. You can think like JSON, but uh, a similar format. And the parcels are passed between the processes. So the kernel is responsible for passing this between processes. Each process runs the virtual machine for the corresponding application. Okay. Oops. Where did my slides go? There they are. Okay. Okay. So we then now come to the notion of permissions, as I was describing earlier, right? When you're installing an application, you get a permission screen where you are asked to approve the set of resources that the application needs access to. So this has changed somewhat in the past few years. Uh, Previously, on Android, all applications used to be static in the sense that you could um, you would get a screen of permissions, and those would be the only permissions that the application requests during its entire lifetime. Now, of course, it's changed. It's a mixture of static and dynamic. You do get these permission screens, but you also get pop-ups in the middle of application execution saying that this application is requesting access to a particular resource, typically something like location or camera, and you click yes at that moment in time. But you can see over here that this is a permission screen where the application has requested um, access to the location. It has requested access to your personal information, which includes things like contact data and so on. And it can both read and write, and it can also communicate over the network, right? So these first three permissions itself are sufficient to, for example, allow this application to read your location and send it out over the network. And this particular application is also asked for storage. So, you can even think about the application as downloading things into the storage from the network. It can also make phone calls and so on. Okay, so yeah, so that's what permissions are. Okay, so every application on an Android phone, it runs inside its own Dalvik virtual machine sandbox. Okay, and each Dalvik virtual machine sandbox is assigned its own unique user ID. So that's how Linux sees it. All of this is built on top of Linux. So Linux sees these unique user IDs as well as the Dalvik virtual machine sandbox executing inside it. And the permissions that are requested by the application to access things like the phone resources are assigned to that user ID. So it is that process in some sense that is sandboxed with respect to the permissions that it has requested. Okay, so this UID remains the same, and this is sort of the static. This is so this UID should not be confused with the actual process identifier, right? The user ID is something that is going to remain persistent and the same as the application. As you restart the application, but each time you restart the application, you get a different process ID. But the UID you can think about as some sort of unique identifier for that particular application, uh, and it remains same across multiple invocations of that application. Okay, so now we have already seen dynamic taint analysis. It's a method, tracks information dependencies from an origin. At the high level, we have seen that there are taint sources from which you taint some piece of data, and then taint propagation, which is statements where taint moves from one variable to the other. From this particular case, if C is tainted, the result of any computation that involves C as a source variable is also tainted, and this is the network sink where something that is tainted is being sent over the network. So the data flow rules are rather interesting, and I would actually encourage you to go and read these data flow rules in a rather uh, uh, great amount of detail. So what you see over here on the left hand side is the Dalvik virtual machine language. Okay, a simplified version of the Dalvik virtual machine language, and this is the meaning of the corresponding operation. So, for example, binary op VA, VB, VC means that you're applying some sort of a binary operator, in this case denoted by the symbol on VB and VC. The result is stored in VA. So what is the taint semantics for this? Well, if either VB is tainted or VC is tainted, then VA is tainted. And that's exactly what this is saying, right? Um, Set the taint of VA to be the union of the taint of VB and VC. So whatever the taint tag of VC is and taint tag of VB is, VA gets the same taint tag. Now, most of these rules are pretty straightforward. We will only look at some which are somewhat non-intuitive. Okay, so we will look at a put and a get, which are array operations. Okay, and then we will um, look at the others. Okay, so this particular case, let's look at a put, which is VB of VC getting VA, right? Which is the VCth index of the array VB, you're storing VA. Okay, so this particular case, you're saying that the state of the array VB depends on the previous state of the array VB as well as VA, which is the taint of the object that you're storing. So if you store an object into a tainted array, the entire array gets tainted. That is uh, taint droid semantics of how they store taint. Now, when you read from the array, right, in this particular case, you're taking the taint of not just the array, but you also want to take the taint of the index. So the index may be used to get some information. The index itself is tainted, that you want to ensure that the resulting value that you're reading from a tainted index is also tainted. Okay, so this is the semantics that TaintDroid is using to propagate taint. Now, uh, here is another one, which is object reference, right? And you're reading a particular field VC, FC of an object VB. And so here you're going to take the taint of both the object as well as that of the individual field of that structure. Okay, so an object may be tainted and its fields have individual taint as well. So the taint of the result of reading a particular field of an object is the taint of the object itself as well as the taint of the field that you're reading from that object. All right, so TaintDroid is implemented as a system-wide taint tracker. Okay, um, if you have got an application that's running inside Dalvik virtual machine, then you track it using these particular instructions, which track taint at the application level. And so all of those taint things happen within this virtual machine. Now, the virtual machine doesn't execute in isolation. It interacts with native system libraries and also applications talk to each other via these binder IPC messages, right? So all of your taint tracking mechanism is implemented in parts in yellow, message level taint tracking, virtual machine, native system libraries, and so on. And so there's method level tracking, variable level tracking, and also taint tracking through files, right? You might store a file from one application, store some sensitive data there, and another application reads from there. Data might pass from one application to the other that way. So you want to track taint through files, and so that is also supported in TaintDroid. So TaintDroid is actually a firmware level modification. It's not an application. Okay. In slightly more detail, this is how it works. So whenever there is an application that's executing, it executes inside the Dalvik virtual machine. That's what you see here as the interpreted code. And so the Dalvik VM interpreter, uh, on top of which this application is a trusted application that has some sensitive data it wants to protect. Uh, the Dalvik virtual machine actually maintains a taint map. So think about the taint map as basically a data structure that keeps track of the taint information. It's the taint label for each object for each object within the virtual machine. So this application may talk to other applications, and as I already said, that happens through this binder IPC library. And the binder kernel module within the kernel, in fact, is responsible for copying things, the taint information, from the source application that's communicating to the target application. Now, within the target application, which could be an untrusted application that you download it from a source that is not really, let's say, the Google Play Store or something like that. The taint is propagated over there, and the trusted library with which the application interacts, it detects whether the information from the taint source is going into some taint sink that is not acceptable. Okay, so that's how TaintDroid detects taint at a whole system level rather than individual program level. Okay, so a little bit more about this notion of variable level tracking. So Dalvik virtual machine, right? It is a slightly different kind of language interpreter in the sense that local variables, they're it's a stack-based language. Okay, so what happens is that you can push arguments. So and whenever you make an operation, a binary operation, for example, it'll pop the top two elements from the stack, perform the operation, put it back onto the top of the stack. So the way that it works is that they actually store the taint tags right next to the object itself on the stack-based language. So it's a taint bit vector that they use and store this information, right? So, and we also spoke about how they store one taint tag per array to minimize the overhead. Okay. All right. So the taint sources and sinks, they must be carefully integrated, right? So you have things like low bandwidth sensors, uh, where location and accelerometer, there's not that much data that comes. So you must ensure that you design your taint tracking appropriately. So there are also high bandwidth sensors like the microphone or the camera. Lots of data comes, the information databases, the address book, and so on. And you have the network, which is generally the taint sink. Based upon the type of information, the taint sources and are carefully adapted. All right, so we'll very briefly look at the experimental setup. So at the time that they did the paper, the app stores were not very big. So out of 1,100 apps that they took from the store at that point, 30 apps were taken, and they carried out experiments. These days, it's routine to see papers that perform studies on 100,000 apps or more. But this paper basically, at the time they did, they ran the applications manually by installing the application and exercising the functionality offered by the application. And then the TaintDroid recorded logs, and they recorded things like TCP, dump network traffic data, and so on. This is how they tracked what the application was doing. Okay, so they found that um, out of 105 connections that were flagged, only 37 were legitimate for reasons the application actually wanted to use. Other applications were asking for these permissions, but the use of these permissions was not entirely clear. Okay, so you can see over here there are a lot of applications that are requesting both GPS as well as permission to make phone calls. It's not really clear why. Okay, and they found that there were a number of applications that were leaking information, right? So two applications were sending out the phone number and number that's private to the phone over to the app's content server. Uh, Device ID was being sent to content servers. Location was being sent to advertisement servers. So these are all extremely uh, interesting findings uh, from the time. Okay, so now we come to performance. As I said, it's a runtime tool. Okay, we'll very briefly look at performance. These are performance numbers that are dated, but the various kinds of things that they look at is the app load time, right? From the time when the application is clicked to the time that the actual activity is displayed. They looked at an application and then they saw, how much time does it take to, let's say, create an account or to read things from a database. What's the time, let's say, to make a phone call, time to take a picture, and so on. And as you can see, there's a little bit of overhead that is added in these applications. These are macro benchmarks, high level benchmarks. They also had a micro benchmark where they look at specific features and then stress test them. And so the standard uh, benchmarks we call caffeine mark. And as you can see over here, um, there is a significant amount of overhead, right? It does add quite a bit of overhead. It reduces the performance by quite a bit as your uh, as you run things on top of TaintDroid. Okay, and this is the performance of IPC benchmarks, the interprocess communication. Again, there is a overhead that is introduced through the tracking of taint tags over the IPC binder interface. All right, let's stop now with some limitations, right? It's a firmware modification. So it's not like something you can install on your phone today to test your privacy. Also, it only tracks explicit data flows. Implicit data flows, where data is flows happen, let's say through conditional statements, are not tracked in TaintDroid. Okay, so that brings us to the end of the TaintDroid lecture. If you have any questions, you can feel free to post on Teams. Thank you very much. Bye.